In this video, we're talking about combinations. This is part 2 of our lesson for week 2 for the intermediate section. And when we talk about combinations, this is a definition for combinations, and this is an arrangement of objects in which order doesn't matter. And that's the key component is we don't care what order they are. We're just trying to take a group or a combination of objects from a bigger group. Another way to think about it is a combination defines how many ways you could choose a group from a larger group. Examples are how many different groups of 20 students could we take from the 150 students in the middle school at Sycamore School? Or how many different, if I got 20 shirts in my closet and I want to take 8 of them with me on vacation, how many different combinations of 8 shirts am I going to take with me? There's no order to either of those. Now you could put order on those problems. For instance, the Sycamore problem is how many different ways could I line up 20 students from the middle school? And so the order in the line would matter. Or you could say for the shirt problem, we did one in the permutation like this, which would be how many different ways could I pick 7 shirts, one to wear on Monday, Tuesday, Wednesday, through Sunday, and that would be a way the days of the week would give the order. So these are problems without order. We have a formula for finding combinations. We use a C for combination, and it's always going to be in CR, and whenever we do that, it's going to be in factorial, very similar to a permutation, right? In minus R factorial, that's just like a permutation, but then we also have to divide by R factorial. Another way to think about this then is instead of writing this, you could write the n permute R over R factorial, which I like to consider it that way because when we're doing a problem, we found the shortcut for permutation is like, for instance, if we did 20 shirts and we wanted 8 of them, you'd start with 20 and multiply down through 8 numbers. And so that's easier than going through this whole process of the factorials, and then you just divide that by 8 factorial. And so there are a couple ways that you can look at this. Things cancel out nicely, but it's good to know the formula for doing that. So if we look at number 1, it says how many subcommittees of 4 can be formed from a committee of 12? And so you got these 12 people that are serving on a committee, and then they need to form a subcommittee, and they want 4 people on it, and we want to know how many ways can we do it. There's no order on this problem because we haven't given the position, anybody on the subcommittee a position. We just have 12 different people. We want to take 4 of them and put them on a committee. So this problem is going to be take 12 people, and we want to choose 4 of them. And so that's going to give us, well, if we did it this way, it would be 12 factorial over 12 minus 4 factorial, which would be 8 factorial over 4 factorial. But again, you're going to have all this cancellation with the 8 factorial, so the easier way to do it is just remember in permute R, so 12 permute 4, which would give you 12, remember you just start counting down 4 numbers, 12 times 10, or 11 times 10 times 9, and then over how many you're choosing, which is 4 factorial, 4 times 3 times 2 times 1. And then this allows us to do a bunch of cancellation. I like to try to cancel out big numbers, so I see 4 times 3 gives me 12, so that's going to cancel that out. 2 is going to go and cancel 10 to a 5, and so you're going to end up with 11 times 5 times 9. You're always going to be able to cancel out everything from down here. On these problems, you almost always cancel everything out from the denominator. So we just need to do 11 times 9, which is 99, times 5, which is going to give you 495. So in this case, there are 495 committees. Now, there's another thing to notice about this. If I would have said how many subcommittees of 8, well, if you write this formula, do it this way, that 12 choose 8 would be 12 factorial. 12 minus 8 factorial is 4 factorial over 8 factorial. And if you notice, these two are the exact same thing. And so it always turns out to be that when you've got these complements, 4 and 8 add up to 12, their combinations are the same. The reason why is if I take a group of 4 away from my committee of 12, there are 8 left over. So by taking out 4, I've also chosen a group of 8. And so that's why those always turn out to be the exact same. And that's something that will be more important later on. We'll talk about how this helps us out and some stuff with Pascal's triangle. Okay, a couple more examples. Example 2, it says in a card game, 5 cards are dealt to each player. How many different ways can a player have all hearts? Well, there are 52 cards in a deck when you're playing a card game. You always want to assume just a regular card deck when you got a problem like this. However, we want to just choose hearts, so we're limiting the what we can get for our cards to just hearts. And there are 13 of each suit, and we want to choose 5 of those to be in our hand. So how many ways can I choose 5 of the 13 hearts? Well, that's just going to be 13, choose 5. And so using the 13 permute 5 over 5 factorial, it would be 13 times 12 times 11 times 10 times 9, and then that's just over the 5 factorial. Remember, this is a shortcut, so 5 times 4 times 3 times 2 times 1. I like to look for things that are easy to cancel out. 5 times 2 is 10, 4 times 3 is 12, and so that leaves us just with 13 times 11 times 9. When you multiply those out, you get 1,287. So there are actually 1,287 different combinations of cards that are all hearts and you could put together. Okay, and the next question says, in a card game, 7 cards are dealt to each player. How many different ways can a player have all one suit? Well, this is a case problem because you got 4 different cases. One would be if you wanted all hearts, all diamonds, all clubs, all spades. So if we wanted to do all hearts, it's just like the problem we did. So 13 choose 7. But there's going to be 4 of these for each suit. So we're actually going to end up multiplying whatever our answer there is times 4. So 13 choose 7 is going to be 13, and we just count down 7, right, using the permutation, because we're canceling things out from our formula. So all the way down to 7, and then we're going to go over 7 factorial. So 7 times 6 times 5 times 4 times 3 times 2 times 1. You really don't need to write the 1. Now we start canceling things out. So the 7s obviously cancel. You got the 6 and the 2, which are going to, well, I don't like that one because it's going to give me a little bit of problem. So, well, we can do that. So 6 and 2 will give you 12. You could do the 5 into the 10, which would give you 2, the 4 into the 8, which would give you 2, and the 3 into the 9, which would give you 3. So that leaves you as 13 times 11, and then times 2 times 3 times 2. So it's going to be 13 times 11 times 2 times 3 times 2, which would give you 1,716. So there's actually 1,716 ways to select 7 cards from it. If you do 13 to 7, but then we need to multiply that by 4 because that's just for one suit. So once we multiply that times 4, we get 6,864. So there's 6,864 different hands that you could get when you're playing a card game, when you're pulling out 7 cards. There are 6,864 different ways for you to get all your cards being the exact same suit. Now, if you wanted to know how many total ways, if you're doing a probability problem, which would be, what would be the probability of being dealt all one suit, you would first have to do 52 choose 7, right? Because your total possible different hands is you got 52 cards, you want to choose 7 of them. And then this is a total that have one suit.